I'm really grateful for having been invited to this conference and being able to address this audience. It all started in Cargese in 1973. That was really a sort of existential occasion, the birth of the renormalization group tribe, I would say. And here I'm grateful to Ariane, Cyrano's daughter, for having provided this very useful picture. This is how Roger would have liked to remember him, I guess, but he is not here, I don't see. And of course, there were many people who were in this room yesterday and today were there. Some of them, unfortunately, are no longer with us, which I would also like to remember. Cargese was truly a meeting of two different worlds, as Jean-Justin has remarked. The normalization group united two apparently totally unrelated domains, the theory of fundamental interactions at the microscopic scale and the theory of continuous macroscopic phase transitions. And I would like to just make a very crude set of remarks, if you like, on the field theory and renormalization group on non-metric spaces, namely arbitrary networks, which do not have to be embedded in any metric space, and the world is now full of this network science, so to speak. And it so happens that one can do some things with these networks, which do not necessarily know at what distance their nodes are from each other, except that they're connected or not. So the Landau-Ginzburg Hamiltonian for a scalar psi, of course, as usual, can be written like this. Instead of the Laplace operator now, we're going to have the Graph Laplacian. Lij, I, and j label nodes. Di is the number of edges coming into the node I, and Aij is 1 if I and j are connected, 0 otherwise. And the field is going to be psi living on the node I, and we can essentially, forgetting about the interaction term, write the Gaussian model in this way. And now we'd like to do a Fourier transform. And how we want to be able to expand the psi I in terms of these psi mu's, and psi mu's are going to be the eigenvectors of the Graph Laplacian. If we can do this, and so the rest is the partition function, and the free energy can be written as sums over eigenvectors, or rather eigenvalues here of the Graph Laplacian. Now, how do we eliminate the degrees of freedom, and how do we rescale? In fact, we tried two different kinds of approaches. I will just present one, which is the simplest, and that is just eliminating the top eigenvalues and keeping only, if there are n nodes, n over capital B of eigenvalues within the calculations. And so you this is the cutoff Hamiltonian, and you would like to now rescale it. And we enter this same B with some exponents to be determined in such a way that this Hamiltonian is now going up to, again, being summed over n different eigenvectors. Now, these rescaling factors can be determined straightforwardly. This V just indicates the first approach that I'm talking about. And This is trivial. You see just the number of eigenvectors being considered here. This is obviously giving phi 1 equal to 1. This is a little bit more tricky. This is entering into the term that multiplies the eigenvalue of the Laplace operator, and that has a phi 2, and we fix the coefficient of the Laplacian term as before, the eigenvalue of the Laplacian, analogous to the k square, to fix the wave function normalization. And here we get something like now the reduced temperature R prime is equal to b to the phi 2 R0, but we have no correlation length ready at hand. We do not know how to relate the rescaling exponents to exponent of this phi 2 to some critical exponent like the nu for the correlation length. So what we did was step back to Kadanoff rescaling and took the appropriate derivatives of the free energy, specific free energy, and in this way we're able to relate, of course with the phi 1 equal to 1, relate the phi 2 to the two different critical exponents for the specific heat and the magnetic field. This is just algebra. And then comes the point where you want to relate these exponents to something of the underlying network, and what is at hand is the spectral density. That's just the this is a log-log plot of the degeneracy of the eigenvalues of the Laplacian. If you just look at this particular segment of the whole plot, that would be a Cayley tree, and this thing is the spectral density for a diamond lattice, it so happens. And we can relate phi 2 to the scaling exponent of the spectral density, and we find for the Cayley tree and the diamond lattice what one would calculate if one didn't do this kind of elimination and rescaling for alpha and delta. Now, the question has been posed very expertly by Ginestra Bianconi and collaborators. Which dimension is it really that determines the critical exponents? And in this particular case, you see that it is the spectral dimension which is defined in this particular way. And adding the interaction terms, one has to do these sums over the sites, or with this multiplication of the different eigenvectors now. 1, 2, 3, 4 just are symbolic for the different these are just different eigenvectors, and one has to sum over all the different eigenvectors. This is familiar notation, I'm sure. And here we have now to renormalize the interaction constant. And it so happens, as you would guess, that the Cayley tree with a spectral dimension of 2 independently of the branching number has a Gaussian fixed point which is stable with respect to first and second order perturbations, and in fact one would expect to higher ones. But on hierarchical lattices with higher dimensionality, and I should really point to the kind of generalization that Itzikson and Luck have presented a long time ago, introducing extra branches or bridges, if you like, between the terminal points, the number of parallel paths p push up the spectral dimension of this lattice. And one would expect that starting, in fact, with the spectral dimension equal to 2, that one would get non-trivial results. However, as this also happens in the perturbative approach of Wilson and company, the non-trivial fixed point eludes this perturbative approach, at least up to second order, at the spectral dimension equal to 2. But the moment that ds is bigger than 2, the Gaussian fixed point becomes unstable. And one has an iterative equation for the value of the fixed point. And, oops, this has sort of slipped. This one-dimensional iterative map gives, in fact, a fixed point which is bigger than 0, although small. And above the spectral dimension becoming 4, this d tilde is also the spectral dimension. Sorry for the switch in the terminology. You find that going from the uncoupled case at 2, as you go up in spectral dimension, after 4, you again end up with a free theory. The sort of joke is that if you compare exact so-called real space renormalization group results for the hierarchical lattice with just the diamond lattice, sort of blindly inserting the correlation length exponent 1 over the yt, the nu in the hyperscaling relation, one gets a rather embarrassing negative alpha, although it is known that the diamond lattice has a real phase transition at a finite temperature. And it is sort of amusing that one can actually write down the eigenvectors of the Graph Laplacian on the Cayley tree analytically, and one can completely work out this problem. We're working on the diamond lattice and the hierarchical lattices. Thank you very much.
Are there questions? Yes?
My question is there the difference between the critical exponents on the Cayley tree and on regular graph, which is...
No, of course, we tried, we verified that we got, for a periodic translationally invariant graph, also the correct, for the square lattice, cubic lattice, etc., etc. With this, you can apply the same steps, so to speak, to any given lattice, and you get the correct exponents. The only time you get into trouble is when the spectral density is not a power law. Then if it's growing exponentially, for example, you don't know what to do. Thank you.